you. So welcome back. So this will be my last lecture. So I'm going to finish up the topics that are here. So when we started this yesterday, we kind of introduced the subject, and we looked specifically at what's unique about astronomical data compared to the natural images or Google image search photos that are really the foundation of a lot of the techniques that we end up using, because it's really industry that's driving a lot of the algorithm development and new ideas. And so it's important, I think the message there is it's important to understand that we really do have, we're working with data, whether it's images or spectra, that are different in some fundamental ways. And there are some missed opportunities if you really just jump in and just use the kind of flavor of the month algorithms that are being used on natural images. Okay, so kind of continuing the theme of unsupervised learning. So the things that we're going to focus on today are kind of the now classic approaches of VAEs, variational autoencoders, and GANs, or generative adversarial networks. And if there's time at the end, I'll talk a little bit about some of the more recent work, which is on things called flow models, and also related to that auto-regressive models. But they're also solving the same problems. We've got some data, how do we build either a generative or probabilistic model of that data? So that means a model that's able to create new random instances, that would be the generative model, or a probabilistic model, a model where you give it a real example, and it will tell you the probability that it came from your initial training population. Okay, so to talk about VAEs and GANs, I want to have a concrete example to work with. So here's a test problem that I'm going to use. So I'm generating some data here. This data actually happens to be a Gaussian process. So I'm not going to explain what a Gaussian process is. It's just a nice kind of scientific, it's like scientific data, because it's and it's a good template for a lot of scientific data, which is why we often use it as a sort of fancy interpolation. But the only thing I want to say about Gaussian process is that since we spent quite a while in the last few days talking about KL divergences, remember that's a way of measuring the distance between two functions. So now, that's already kind of stretches us a little bit. But now I want you to imagine not just a distance between functions, but a probability distribution on functions. Okay, so probability distribution is a function, but now we're going to have a probability distribution on functions. So I give you a function, a whole PDF. Okay, so why does an autoencoder not have the same weights on the two sides? Yeah. Okay, that's a good point. So there's a lot of kind of permutation degeneracies here. So that's one reason, but there's actually a more fundamental reason. So even they will not even have the same weights under permutations. Someone else want to? Okay. Uh, Not necessarily, I don't think. So, okay, there probably will be, yeah. But even with a small number of parameters, there's something breaking the symmetry, right? It's architecturally symmetric.
Yeah, so my idea was that in the end, when you're learning the encoder and decoder, you're learning basically two matrices that are projecting onto a lower dimensional space. And if you and the direct transformation and the inverse are not the same matrices, so the weights would have to be different.
Okay, but all these answers are telling me you're thinking about this as linear. Okay, fundamentally, I mean, this is crucial. Neural networks are nonlinear. And the way the nonlinearity comes in, it breaks the symmetry. Because basically, if we just had one layer here, you've got some linear piece here, and then you've got a little bit of nonlinearity right there. And then you have another linear piece, right? So what's the smallest nonlinearity we can, kind of the mildest nonlinearity we can put into a neural network? So I'm basically talking about activation functions. Sigmoid is very nonlinear. It's all. Yeah, right. So a linear activation is that, and then the kind of the most trivial nonlinearity is ReLU like that. But that breaks the symmetry. Okay, and typically you'll have it's not just here, but it'd also be at various places in here. But it's always you have like something linear, and then you have a nonlinearity piece, and then, right? But the ordering is different. So that breaks the symmetry. And so you have, so I mean, you made some good points about the permutations, things like that, and that's also an issue. But yeah, so that breaks the symmetry. And so you expect completely different weights. Although they have the same, essentially the same architectures, you always have the non-linearity after the linear piece. So that doesn't get flipped. Okay, so this is related to the answer to the other question. How would you build an autoencoder to perform classical PCA? Yeah, you just put in linear activations or just take the activations out entirely. And in fact, try it. It actually works remarkably well. You can use TensorFlow or PyTorch to do PCA. You get essentially that's all it's doing at that point. And it won't matter how fancy you get in your layers here, because as long as you have no nonlinearity, a sequence of linear layers is just equivalent to one big linear layer, okay, modulo round-offs and round-off errors. So. Okay. Yeah, so the fact that neural networks have nonlinear pieces is essential to how they work. Because effectively, I don't really have time to talk about this now, but there's the key idea here is that you're doing something called the kernel trick. And you're basically, by putting this nonlinearity, you're projecting the space that it's working into something much higher dimensional. Where even if the data was dense in the original space, it becomes very sparse. And that's really what makes, once you've boosted into that higher dimensional space, then just linear operations can capture the structure much better. And it's kind of remarkable. I mean, people originally used sigmoids and kind of fancy nonlinearities, and then eventually realized that it's just the smallest nonlinearity is enough to get this, to trigger this kind of kernel trick process. Okay, so something to read about later if you're interested. So, and actually in my lecture notes for the course I teach at UCI, there is a little notebook on nonlinear, basically taking linear methods and using this kernel trick to boost them into a higher dimensional space. I don't think it changes any aspects of what I said, but it is a problem. It is a challenge that we have to deal with, because often in our data we understand the noise in our data in the input space, and it has like nice Gaussian or Poisson form. But as soon as you put it through any nonlinearity, then it just becomes, you can't really model it anymore. And so you would like to be able to kind of propagate it through to the loss function, so you can actually have a principled loss function that knows about the noise. But that's actually really hard to do once you have some nonlinearity. So. Okay, so the other thing I want you to think about, and actually I think I'm just going to show you the answer so we can keep moving, is I talked about probabilistic models and generative models. So once you have this distribution, and maybe you just get this from PCA, so how would you then tell me the probability? If I give you a new point and I tell you where it is in each one of these plots, how would you estimate its probability of being from the original sample? So you need some way of assigning a probability. You can think of this as just like the output of a Markov chain, what we've got here, right? So I need to fit all of these blobs to something nice and smooth that I can normalize, and then I can tell you a probability. Okay, so kind of the two classical approaches would be kernel density estimation. Right? I could just make a little Gaussian blob around each one of these points, sum them up, or else I can fit the blobs overall to a mixture of a few Gaussians, a Gaussian mixture model. So those are kind of two classic density estimator approaches that are both easy to use in scikit-learn. And so I would feed in these points, and it would then give me, and then I could just feed in new points, and it'll tell me their probability or their log probability. So that is a probabilistic model. So you can make a probabilistic model just from PCA or an autoencoder. If I want to make a generative model, I need to do one step further. So once I've got fit this to a Gaussian mixture model, then I just generate random numbers from that Gaussian mixture model. But I'm not done, because I want to generate things in the data input space. And here I'm generating things in this 6-dimensional latent space. So to go back to the data space, I need to use the expanding part. So I'm generating random numbers here, and then I need to feed it through this part here, and that will put it back into the data space. Or if we're just doing PCA, I need to just multiply y times m, those two matrices. Okay, but there's nothing, these ideas of generative and probabilistic models, they're not really, they're not new ideas or specific to neural networks. You can do them just as well with PCA. Okay, so a lot of the recent progress in unsupervised deep learning has been to invent neural network architectures that can do those things, tell you the probability of some new data, or generate something that looks like new data without going through the steps that I just described, where you get a bunch of samples, you fit it to a Gaussian mixture model, you do some sampling. So basically you want to bake all of that in to the neural network and have it all be self-contained. But so it's really solving a problem we couldn't solve before, but it's trying to solve it kind of in an all-in-one, holistic way. And the goal of that is not just to do the same thing differently, but to actually make better use of the available input samples. So you want to make it less likely to memorize a small training sample. Okay, so variational autoencoders. So both GANs and VAEs do something important, and that is they break this connection right here. Okay, so we're not going to have a direct connection. The data will never flow directly through to the output. So we're going to use different ways to break that right there. So this is the architecture for a VAE. It looks quite complicated because I'm really showing you all of the plumbing here. The main thing, we're going to come back to this several times, and the main thing I want you to notice the first time through is that, okay, it is an autoencoder in the sense that it has the same input and output shape. There's no direct connection in the middle here, like I just said. And it is reducing, right? We're going from a big input space to a smaller output space. And then here we're going, and on this other half, we're going from the same sized small latent space back to the input space. Okay, and we'll notice some terms here, KL, elbow. Okay, so that's the V in VAE. Okay, so the way we break things in the middle here in a variational autoencoder is that instead of taking the input and mapping it to a point in the latent space, we're going to map it to a distribution in the latent space. Okay, that sounds really fancy. I go from a point to a distribution. That's like some function. But if we pick a concrete family of distributions, and usually we pick the Gaussian distribution, mapping to a distribution really just means picking a value of mu and sigma, if we're in 1D, or a mu vector and a covariance matrix. And those are just numbers. Okay, so although we say we're going from an input point, or input vector, to a distribution, we're really just going from an input vector to a parameter vector. So in particular, if I'm going to go from, in our case here, we have 128 inputs, and I want to go to a 6-dimensional latent space. So that means I need a mu vector that has 6 numbers and a sigma vector that has 6 numbers. I'm just assuming it's a diagonal covariance. Okay, so really, when you get down to the nuts and bolts, all that's changed is we're going from 128 to 6 and 6 instead of 128 over here to just 6. Okay, so we're just doubling. We're going to 6 plus 6 numbers instead of just 6. Typically we do this actually kind of with 2 parallel neural networks going from 128 to 6 and 128 to 6. Although you could do it as 128 to 12. It doesn't really matter how you get the 6 plus 6 numbers out. So what does that distribution represent? So that's what I'm going to explain. But the reason it's labeled here is because really what that distribution is it's the posterior in the latent space. Okay, so this is a kind of a Bayesian construction that we're talking about. Okay, so once we've broken this connection, so how are we going to then get back into the input space? So we need something to compare. We're still training the network as if it was supervised. So we'll take our input and we're going to feed it into the loss and compare that to the output. So we need to make an output that looks like the input. So the trick is what we're going to do is we're going to generate random points in the latent space. And then we'll use the same expanding network to go from the latent space to the data input space. Okay, and that's how we'll get something that at least has the right shape to put into the loss function. Okay, so the thing that feeds this is just a random number generator. Okay, so because we're introducing randomness here, we go from input to mu and sigma, which is just describing a distribution, and then we sample from a Gaussian that has that mu and sigma and feed that back out. We can't really expect that the output is going to look just like the input, right? We went to a distribution and then just picked a random point from that distribution. So they're statistically related, but they're not going to be. They could never be the same thing. And so the key insight of the VAE is that what we're actually doing here, what I've described, is actually a type of variational inference. And once we've made that then that tells us exactly what the loss function should be. Okay, so remember, the loss function for variational inference, the thing that we want to minimize is the negative elbow. And that just has 2 pieces. It has an L2 loss that says how well our parameters explain the data. Parameters Z explain the data. And then the KL divergence of our approximating family with the prior. So several of you asked me after I talked about variational inference, you said, okay, that's all very good, but how do I pick an approximating family? Right? And so what we're doing here is our approximating family is just a neural network. Okay, so it doesn't have to be something that you look up in a dusty textbook, some classical function named after some German mathematicians. It's just it can be a neural network. It can be your approximating family. Remember, an approximating family it's a function of 2 things when we talked about variational inference. We talked about Q of theta, and then the variational parameters S. So here, the theta is actually our latent variables, Z. And the variational parameters, the things that we're going to use, remember we're moving around this space of Q. S is what moves us around this space of to give us different values of Q, and then we're trying to find the one that's closest to the posterior. So the variational parameters are just the neural network weights and biases. So once we've constructed a loss that approximates the elbow, we're going to, that will effectively, as we train the neural network, that's going to move us around this space parameterized by which is just different neural network for the same architecture, to find the neural network that's closest to the posterior that we care about. So we're going to have to specify a prior here too. So that's represented down here. And what we do is we use a Gaussian prior, and we actually we fix the parameters of the prior. We say the prior is just a unit Gaussian. It has 0 mean and standard deviation 1. Okay, well that doesn't sound very Bayesian, because the prior is supposed to be, you scratching your head for over the weekend and trying to figure out, what do I really believe about this problem before I've seen any data. And here I'm just saying whatever the problem is, we're always going to choose a prior that's just a unit Gaussian. So we're turning things a little bit around here. Okay? We're actually we're saying we're starting from a prior because we haven't specified what the latent space is. So we're actually going to fix the prior and then learn the latent space for which that is the right prior. Okay, so I'm going to come back to the theory, but before we get lost in that, I just wanted to kind of just show you this is really just a practical thing. So here I've built a VAE. I say we've got 128 inputs in the data, and we want 6 latent variables. There's a hidden cell that shows you how I built that with using PyTorch. And now, before I do any training, all I've done is just constructed that thing. So here I'm asking it to generate some samples. Okay? Remember, what it should be spitting at when it's working well is those nice, smooth Gaussian process draws. Okay? They don't look anything like that. It just looks like noise. Okay, it's not surprising. We haven't seen any data yet, so it hasn't had an opportunity to learn from the data. Okay, so here I'm doing the training. I'm just showing you the test data here because I want to show you how it breaks down. So the actual loss that the optimizer is seeing is the minus elbow here. That's the green. But the minus elbow is actually calculated from 2 pieces. We build a tensor graph that has 2 separate terms to it. It has the negative log likelihood, which is just comparing each input sample with the random output sample. So that's getting better and better. And then also the KL, which is measuring how similar our fixed unit Gaussian prior is to how similar our approximating family is, this part of the neural network, is to the unit Gaussian prior. And that actually starts out really good and then gets worse and worse. So what we're doing is we're getting this competition between explaining the data and matching the prior. Remember I said that's really the key to having optimal Bayesian learning. And so the story this is telling us is that when you start out, it basically, all it knows is the prior. It hasn't seen any data. So it just generates samples that look exactly like the prior. And then as it goes on, but it does a really bad job explaining the data. As it goes on, it gets better and better explaining the data. And it moves away from the prior. So that means we have informative data. And then they sort of reach a compromise here where things are relatively flat. Okay, that's how to interpret that plot. And if you are training VAEs, I think it's important to look at separately those 2 components, although the actual optimizer is just seeing the green. So that it's the gradients of this that are getting back propagated through the network to update all of the weights and biases. Okay, and so now here, these are, after we've done some training, then this is what happens when we ask it, if we just feed in some random numbers at this point here, and then push them forward to get to the output. So now it's basically able to take, the random numbers are just samples from the prior, just from a unit Gaussian. So I'm just generating in 6 dimensions, I'm just sampling from a 6-dimension dimensional unit Gaussian. But then when I feed it through this network here, it has learned how to turn pure noise, pure Gaussian noise, into things that look like the data. Notice it actually has some noise here. There was no noise in the input data. So that's not noise coming from the data. That's actually noise added. So it hasn't learned to. It's basically added some noise-like variance. Yeah.
If we can have few samples also in a classical autoencoder, so why doing this fancy projection onto a function or a space of functions if you can just do KDE on the latent space of a classical autoencoder?
Yeah. Okay. So, I mean, we're doing a simple kind of pedagogical test problem, and so if I was writing a paper showing this, then it'd be very important that I also said, by the way, this is basically no better than we can do. In some senses, worse than with a PCA or just a simple autoencoder. You're right. Yeah. But the reason why that's not true of all papers is because the important thing we're doing here is that we're splitting this thing right here, and so that really makes it much harder for the network to overfit, right? Because you never have things flowing, the data flowing all the way through. So in this case here, that's not really limiting us, but it generalizes better. Just the architecture itself intrinsically generalizes better. So for more richer problems with more complex data, then. Yeah, yeah.
You don't have any distribution. You have infinite mappings between the data and the latent space. So you can have two objects very nearby in the latent space, but very different in the data space.
Yeah, that's a good way of thinking about it. So the way to think about the latent space for variational autoencoder, let's just say we have a two-dimensional latent space, a Z1 and Z0. So where we have the prior, and we just declared that that's going to be a unit Gaussian. And what the reducing part of the network is doing is it's taking each data point and it's mapping it not to a point in the latent space, but to a mean and a sigma. So how do we represent that? It's just a blob like that. So this would be a particular point gets mapped, some particular x gets mapped to this z. Okay, so what this is that's the posterior. So here's your prior, which you just fix, and this is the posterior for that particular piece of data. So if I put in another piece of data, which may be very different in the 128 dimensions, but it could end up being right next to it in the latent space. Okay, but in the latent space we're getting a Gaussian blob for each input data, not a point. And then when we expand, we're sampling from that Gaussian blob and turning that back into something in the data space that we'll put into the L2 loss.
If you want to use PA for unsupervised clustering, doesn't this prior works against us? Do we have a multimodal prior or something like that?
So there may be some multimodality in the data, but we're kind of turning things around because we're saying we're declaring this is a prior, but we haven't specified the mapping between the input data to latent space. So we're learning that mapping such that was the appropriate prior. So the multimodality would have to get learned in the mapping. Yeah. Yeah, that's a good question. Okay, so the first part of the network is basically taking each sample and then just mapping it to a little Gaussian blob, like I showed you there. And so that is then so our approximating family of functions is just the neural network. These are the biases and the weights, and then these are the latent space variables. And so we're using variational inference to make this approximating family as close as possible to the posterior for each data point by learning the neural network parameters here. Okay, so we are finding a variational approximation. So it's an example of variational inference. So that tells us what the loss should be. It should have a piece that calculates that answers the question, how well does our latent model explain the data? And then a piece that says, how well does our approximating function look like the prior? We don't want either of one of these to dominate. We want to have a balance between them. It'll find the appropriate balance based on how informative our data is. Okay, so the first term of the minus elbow, that's just the negative log likelihood. It's an average. It's an ensemble average. And we just draw parameters. Once we've got that little blob, we're just going to randomly draw numbers from it and then pass that through the expanding part of the network. So remember, we use ensemble averages to replace the integrals in the KL divergence. And so how many samples should we make from this little Gaussian blob in order to get a good approximation to that integral? Well, probably a lot. But in fact, what we do is kind of extreme. We only take one sample. And so that is going to be noisy, right? That's going to give us a very noisy estimate of the Monte Carlo integral. But this is kind of a theme in the way we do optimization in deep learning. Okay? The whole idea of using mini batches, instead of using the whole data every time to update the weights and biases, we just use a small piece of the data, which introduces noise, but it lets you go through much faster, and it helps mitigate the fact that GPUs, you can't actually usually fit the whole data set in memory at once, so it's kind of solving a practical problem. But it also has a theoretical advantage, and is that when you have some noise in your loss function, it actually acts as a regularizer and helps. It helps generalize. It's kind of like a temperature. You've added some thermal energy to your minimization, and so it helps avoid that you overfit to the data. Because basically, every time it sees the data, it's just seeing a different view of the data, a different subset of the data, and so it's always looking at a moving target, and it can never really memorize the data. It's the way to think about it. So in practice, we do that Monte Carlo estimate with just a single sample from that posterior. So what's the likelihood of so the first term, we need to estimate the likelihood of the data given the point in the latent space. So we use the second part of the network to go from the latent space back to the data space. And then so a sample is going to have a high likelihood if it can be accurately reconstructed. So what's the chain? We start from some input data. We map that to a mu and sigma, a little blob in the latent space. And then we draw a random number using that mu and sigma in the latent space. And then we feed it through the expanding network. So that's what we get here. And so we're just going to compare the input value to the output value. Because we've drawn a random number, they're not going to be a great match. But that's the right way to frame that term in the variational loss. So we need to somehow measure how well x out and x in agree with each other. And so there's different ways of doing that. We usually use the L2 loss, but you could use L1, whatever. But one nice thing for scientific applications is that we often know from first principles the variance in the input data. And so there's an opportunity. We can actually do a kind of a principled loss here. We can actually calculate a real chi-squared instead of just a mean squared error loss, right? And so we could take into account, for example, our knowledge that certain features in the input are well measured and other features are poorly measured, right? So if we have an image, there might be some pixels which basically have a zero inverse variance because there was a cosmic there that was we masked out the data. So you can propagate that information through. We talked earlier about how the nonlinearities can mess up the error model, but we don't have that issue here because we're working purely in the input space. So what your knowledge about the uncertainties in the input can be used directly here to calculate a proper loss here. Okay, but often we don't have just simple Gaussian errors in the input, and so that approximation of making a chi-squared isn't strictly true. But we still, VAEs you almost always use an L2 loss, even if that's not the right uncertainty model. But at that point there, you don't really have any first principles knowledge of what the errors should be. So that factor, 1 over 2 sigma x squared, which tells you the right way to weight the two terms in the elbow, now just becomes an arbitrary hyperparameter. Okay, so the second term in the elbow, which says it's measuring the KL similarity between our approximating function represented by the reducing neural network and the assumed prior, just a unit Gaussian. Because everything's Gaussian, you can actually do the full KL integral here just analytically. So that's the formula for it. So that's kind of a strong reason to use Gaussians for these things. So we don't have to do another numerical integral. Okay, so that thing so doing the analytic integral, that's what's going on right here. It's just a formula. It involves the mu and the sigma of the prior, and the mu and the sigma for the data sample that we're just looking at here. So that's the KL parts of the elbow, and then the loss here, I described the chain for the input, goes through to the mu and sigma, generate a random number to sample from that, and then expand. So that's our L2 loss. We put those two together, and then the elbow. So as I said before, by fixing the prior to a unit normal, we're really turning things around. And so we normally build a defining the parameters, and then the parameters, which is basically defining what we mean by z, and then choosing a suitable prior based on our understanding of the problem. Here, we're specifying the prior, and then we're learning and mapping from input to latent variables that will explain the data with that prior that we've fixed. Okay, so you're allowed to do that, but it's not the way we normally think of things. And then finally, the red path here. This is saying, well, once you've done all this, really the useful thing that's done after you've learned all of the weights and biases is that we can generate random samples. And so the way that you generate random samples is shown with this red path here. Okay, so at that point, you throw away this input part. You just generate random numbers from a unit Gaussian. Okay, you're sampling from the prior, and then you feed those samples through the expanding network, and you get out random samples. So the second part of our network is something that goes from the latent space to the data space, and we're just going to sample from our prior to get unbiased, unconditional samples. Okay, so any questions? Now I'm going to talk about GANs. Any questions on VAEs before we? So I'm sure a lot of you have used VAEs without really appreciating, a lot of the kind of theoretical underpinnings, and yeah. Yeah, so what you'd like to do is, so there's a whole, there's other distributions where you can do this integral analytically. So you'd probably want to pick one of those. But if you don't, then you'll need to actually then do a Monte Carlo integral estimate of this piece here. So that will make it much less efficient. But yeah, there's nothing, you can have this structure. So the key things are for efficiency that you can do this integral analytically, and that at this point here, you can use something called the reparameterization trick. So if you haven't heard of that, just look that up. But there's other, Gaussian is just one distribution where you can do that for. And even if you throw away both of those assumptions, there are still methods that will do it, but it's going to be a lot slower. So.
Why would you draw from the prior even to make the sample? You should draw from a KT of Q, right? Because the Q might be the same.
No, because the prior, so if we're drawing unconditional samples, so they're not conditioned on anything. So that, an unbiased sample is should just be you're sampling from the prior, yeah.
What would be the difference if we just use the Gaussian mixture model, Bayesian Gaussian mixture model to try to match the latent space?
That would be kind of just a fancier version of PCA. You would still be have a direct connection from the inputs to the output. So, but it's a perfectly sensible thing to try, And so that's why I think it's important that you always compare different methods and really study. It's really what you learn about how the advantages and disadvantages of this technique versus this technique. That's the useful in a paper, I think so. Yeah, so I'm not trying to sell this as as the solution to all problems at all. Yeah.
How do you measure that if another input data is well produced by the model, the probability of being produced by the model?
So what you could feed in to some new input and look where it comes into the latent space, and then compare it to the prior. So if when you map something to the latent space, you get a mu and a sigma that's out here, that would probably be that would be the signature that it was unlikely. Yeah. But this is not really set up. This is not really geared towards answering that question by basically doing probability. So. Okay, so GANs. So GANs are fortunately a little simpler to understand theoretically, and so I'm just going to kind of walk you through the traditional kind of the historical development and understanding of GANs, and then show you at the end that GANs are actually under the hood have recently been understood to be something quite not so different from a VAE in the sense that there is actually a variational problem that's being solved, though this was not really appreciated when they originally developed. And it's related to that symmetrized KL that we had a little bit of discussion about yesterday. Okay, so a GAN has two separate models. Again, we're breaking the connection here. But the architecture is kind of different. We're taking those two pieces, splitting them apart, but then actually taking the expanding piece and putting it on the left. That's why I've drawn it here. So there's two completely separate models, and so that means we're going to be training two different networks in parallel. Okay? Although we had two pieces to the loss before, we had the L2 piece and the KL piece, they came together to make a single loss. Here we have two different networks and two different losses, and we're going to see that makes it a little fragile. And so classifier. And then we have a generator whose job is to take a point from the latent space and map it, expand it into the data space. So that's just like the second half of the VAE or the second half of an autoencoder. And then what we're going to do is we're going to feed random numbers we're going to generate random points in the latent space, and we're going to expand them with the generator. So those are just going to be fakes, right? That's not real data because it's just coming from random numbers. And this thing, you will never show this part of the network real data. So it's never going to directly see real data that it can learn from. And so we'll feed our fakes into the discriminator to see how good the discriminator is as recognizing them as fakes. But we'll also feed real data into our discriminator to see how good it is at recognizing real data. Okay, so our discriminator is going to be seeing both fake data coming from the generator and real data, and we're not going to tell it which is which. So we're going to randomly initialize both of these networks, the discriminator and the generator, and then we're going to have to carefully train them together so that they're both going to gradually improve together. And so for each mini batch of the training data, we're going to generate a corresponding batch of fake samples, and then we're going to use the discriminator on both the real and fake samples. Okay, so I've got a mini batch of data. I'm going to feed it in here, ask the discriminator, is it fake or not? And then I'm also going to generate a same size mini batch of just completely random generated data. So those are fakes, and I'll ask the discriminator the same question. So I want the discriminator, so I want to reward the discriminator for correctly identifying both the fakes as fake and the real data as real. So I need two loss functions. So the discriminator loss, as I said, rewards correct classification of fakes as fake and real. And then the generator loss, we reward the generator when it's able to fake the discriminator, when it's able to trick the discriminator. Okay, so we give it a pat on the back every time it feeds something to the discriminator. The discriminator doesn't spot as a fake. And just as with the VAE, the thing that we're really after here is a generator part. The discriminator is kind of mostly just a technical means to getting a well-trained generator. And like the VAE, the GAN is relatively immune to overfitting because the generator, which is the thing that we're going to keep and use later on in other applications, has never been fed real data directly. It was only ever fed random numbers. So it's just learned how to turn random numbers into things that look like plausible data according to the discriminator. Okay, so to build a GAN, we just need to specify the architectures go from 128 to 6. We have a similar number of parameters in both of our networks, but they are 2 separate networks. Before we've done any training, if we evaluate some data, again, we just get random noise. It doesn't know anything about what the data looks like. So here, these are outputs from the generator, and these are the probabilities that the discriminator assigns it. So basically, it's the discriminator is hedging. It says everything is 50% likely to be real, because it hasn't learned anything yet. These are real data, and the discriminator also says that those are all about 50% likely. Okay, so it hasn't learned anything yet, but kind of not. So this is sort of our starting point. And then to learn, we're going to have to, we're updating these 2 losses. We're back propagating simultaneously through 2 separate networks. And for learning to work, you have to carefully maintain a balance. You have this arms race going on. The generator gets slightly better each time, and the discriminator gets slightly better each time. And so a good diagnostic when you're trying to train GANs is to plot those 2 separate losses. This is again on a log scale, and what we see is that they tend to be anti-correlated. So, here the generator has a large loss. It's not doing so well, and the discriminator is doing better. But then they converge together, and so this is what you want to see when that balance is working pretty well. And you need to specify separate learning rates because we really are training 2 neural networks in parallel. Okay, so to illustrate how fragile this is, so I had to tune those learning rates by hand to get this to work, and this is a pretty simple problem. But if you change it, so here I just increased both learning rates by a factor of 10. So this is an example. This is what it looks like when it's not working. So these start out about 2 orders of magnitude apart, and they stay 2 orders of magnitude apart. Okay, so it's a little hard to interpret this. A better way to diagnose what's going on here is to make those same plots that I had before. So this is after you've done a whole bunch of epochs of training. I ask the generator to give me some samples, and this is what it gives me. Notice how the 3 different samples are very correlated. They're almost identical. And the probability that it's assigns for each one of these is essentially 0. Okay? And then this is real data. This is what we're trying to learn to generate. And it says the probability of these is 1. So what would you say? So the question you want to ask when things aren't working is, well, which one has kind of won the arms race? Right? We want to have like a Cold War standoff here. We don't want one superpower to just quickly win. So which is it, the discriminator or the generator that's won this? It's the discriminator, right? Because the discriminator is perfect. It says that those are 100% real, and these are 0% likely to be real. Whereas the generator is still in kindergarten here. It hasn't learned anything yet. So, in fact, it's even worse than random because they're fully correlated. It's basically spitting out almost the same thing every time. Okay, so this is much easier to interpret than the loss curve. So I recommend you kind of do some training and then look at diagnostics like this to figure out what's going wrong. So, and then you want to think about how to adjust the learning, either the learning rates or the batch sizes or stuff, to give in this case here, you'd want to give the generator some sort of advantage or somehow handicap the discriminator. Okay, so there's a lot of mystique about training GANs, but I highly recommend if you're in this business. So there's a really nice talk and an accompanying GitHub repo with a lot of practical advice on training training GANs. Right? When people write papers, they rarely mention like what are the essential things that actually made it work. They kind of focus on the theoretical highlights, but there's a lot of practical details. And so what this author did is he really went through, he looked at people's GitHub repos and really scraped out what are the actual important ideas that make these things work a little bit more robustly. So this is essential reading if you're working with GANs. So. Okay, so the VAE and GAN architectures, they both learn a generative model. What I mean by that is that once you've trained them, you're going to throw away part of the network, and the thing that you're going to be left with is something that you feed in random numbers, and it will spit out things that look like they came from the original training sample. So it's a generative model. And so we've seen that the VAE is, the loss of the VAE is basically it's the KL divergence. So it's measuring the similarity between our approximating family, which is a neural network, and the true posterior. And then there's a constant, which we don't care about in the loss. So long after GANs were developed and had been used for a while, people realized that you can write the loss of a GAN as also as a type of divergence. So it's also the divergence between the generator and the true distribution of the data. But it's not the KL divergence. It's something called the Jensen-Shannon divergence. So the Jensen-Shannon divergence is it's a particular way of symmetrizing the KL divergence. Okay? So we actually, in variational inference, we like that the KL divergence is asymmetric because it lets us make all of our, to replace all those integrals with Monte Carlo estimates just using samples from Q, which we pick to be something we can easily sample from. Okay, so that in that sense, we want the asymmetry is not a bad thing for variational inference, but it's also theoretically it's a little awkward that you have a distance which is asymmetric. So it turns out that the GAN is actually minimizing this particular symmetrized version of the KL divergence. So it's symmetrized because we take the KL divergence between both Q, the generator, and P, the true distribution of the data, with respect to a third distribution, which is just the average of P and Q. Okay, so it's not the only way you could symmetrize it. We talked about doing a product. You could just take a straight average of P and PQ plus QP, but this is something a little different. So I think another important development is that there's, completely independently of KL divergence, there's another important type of metric. There's something called the Wasserstein metric, and this really is a metric. And if you've heard of Wasserstein GANs or W GANs, so they basically replace they are minimizing this Wasserstein distance. Just to motivate why we one of the main benefits of the Wasserstein GAN if we have one-dimensional probability distributions with the KL divergence, these two distributions here, they have an infinite divergence. And it doesn't matter, if we move this along sideways, get closer or further away, there's always infinite. And so there's no information there in the distance to tell you how close these things really are. Right? Obviously, if this thing is parked right next to it, that's better than if it's way over here. So the Wasserstein metric is actually, it doesn't have that property. And as you move this closer together, even though they have no overlap in their supports, it will get smaller and smaller. And so it allows you, when you have problems where you start out with really, your approximating family is so far away that there's essentially no overlap, it will still, the loss will tell it how to get closer and closer until it does overlap. Okay, so it's a lot more robust because you don't need to start from such a good approximation. The reason it's called the Earth mover metric is because one way of thinking about what it does is if this is one probability density and this is another probability density, then the Wasserstein metric is basically, you can think of it as the cost of coming in with a shovel and taking each piece of, this is a pile of dirt now, and you take each piece of dirt and you move it to somewhere to build this new pile here. You're reforming a pile of dirt from one shape to another shape. And it is actually the integrated cost of reforming that, where the cost is just the sum of the moves. How far do you have to walk with your shovel each time? Okay. So finally, a bit more tangible probability distance. So. Okay, so there has been a lot of recent work. Initially, VAEs and GAN started out as very kind of different motivations and seemed like very different beasts for building generative models. But I think now there's a realization that they're really both examples of a pretty broad family of generative models. And so now in the literature, there's quite a lot of VAE, GAN variations on each of these, but also hybrids of them. And so I think the definitive reference right now is this thing called the Vegan Cookbook, VAE, GAN. So there's the Vegan Cookbook, which is a nice paper that really explains kind of the theoretical connections between these, and also talks about how to bring in other metrics like this Wasserstein metric. Okay, so if I was doing another lecture, I would focus it on kind of some of the recent developments in generative models that are kind of independent of all of this VAE GAN direction. And that is really focusing on building from first principles a probabilistic model rather than a generative model. So I just wanted to briefly sketch out the idea here so you have something to get started reading more about this. So you'd probably notice that both the VAE and the GAN have these fairly complex loss functions. For the GAN, we even have two loss functions. So why don't we just simplify, start with a simple loss function and just maximize how well the model explains the data. Okay, just do that directly. And so we'd like to have a loss function which would be where we're optimizing just a plain negative log likelihood. We want to calculate the probability of each input of each output given the parameters. And so the problem with this is that we don't know how to estimate the log likelihood of each input sample. Okay? A network, the data flows through, but it just gives us an output, not a probability. Okay, so the idea of a flow-based model is we want to make a neural network that will actually calculate, instead of data in, data out, it's data in, probability out. Okay, but you have to have a special architecture that's going to do that, because some random function will satisfy the requirements for being a probability density, right? We want a network that is a probability density itself. So to be a probability density, you need to make sure the value is always positive. Okay, that's actually trivial to do. We just put ReLUs on the outputs, for example. But the hard thing is we need to make sure that the integrals over the full domain of the data space is equal to 1, right? So that means if we were to feed in a large representative sample of data and add up all of the values that come out, that they would always equal to 1. And we need to maintain that while training as we vary the weights and the biases. So the key idea of a flow model is that you're going to start with some simple and analytic base probability that you get to choose, call it Q, and that's usually going to be a multivariate Gaussian. And then you're going to slowly distort it to better explain the data. So it's kind of like with the VAE, we just said, okay, I'm going to declare that my prior is a Gaussian, and then I'm going to figure out a latent space that explains that. So here we're going to declare that in some latent space, our data has a Gaussian distribution. But then we're going to morph that Gaussian distribution through a series of transformations until it actually looks like the data. Okay, so first we'll start with some very symmetric, we'll add a bit of a tail, and then we'll start to add other peaks and valleys. And so that's the kind of the plan here. And so now the network, instead of having to calculate a probability, which is hard because it's very hard to satisfy this requirement, instead we start with something that already satisfies these two requirements, and then we distort it. So the network's role is to distort, to go from Q to the space, the latent space, to the space of the data. Okay, so the way this works is our data is drawn from some unknown probability distribution, and that's on this side here, the data. We're going to have latent variables that are sampled from some known distribution, and then we have a neural network that tells us how to go from the latent space to the data space. Okay, so the neural network is this thing right here. It calculates the transformation from latent space to data space. Okay, and there's no reducing here. This is the same size as the data. So I shouldn't really call it latent space. That's why I called it Q, not Z here. Okay, so in order for this to work, we need to also be able to invert this function. So we still have, that's a pretty strong restriction on our neural network. Our neural network has to calculate something that's invertible. Okay, because of all the nonlinearity in a neural network, that is not going to happen automatically. So, but as long as it is invertible, then using some calculus, we can calculate what the log of the probability of the data is. It's going to be the log of the probability density for this thing here. I'm missing an extra parentheses there. And this we can calculate because we get to choose Q. It's just a Gaussian or some simple distribution. But the hard thing is that we need to be able to evaluate not just F, which the neural for us, but also F inverse. Okay, so we need F inverse appears two times here. Plus we have this determinant. This is a matrix with the determinant of the matrix. So in order to have a network that can morph a simple distribution to the actual distribution of our data in a way that we can now calculate the probability of the data, we basically want to propagate the easy to calculate probability here into the hard to calculate probability here. But it's just a change of variables with some Jacobians. So we need a neural network that's invertible, and both the inverse and the Jacobian determinant of its inverse have to be efficient to calculate. Okay, so we started out with some impossible criteria that we had to be able to normalize probabilities, and now we've got some not impossible, but still not easy criteria to satisfy. But this is doable. So there's a lot of active development research going on in this area. So if you've heard of models like Real NVP, NICE, GLOW, MAF, IAF, so these are all examples kind of along this theme. And what they all have in common is they take this kind of the transformation from simple Gaussian to realistic data distribution. They break it down into small pieces. Each of those pieces has some learnable parameters, and each of those pieces is invertible and has a Jacobian determinant that you can calculate. So if you've heard of autoregressive flows, is a way of basically pruning like eliminating some connections in your neural network to and the fundamental difference with this whole family of models is that these are not generative models. These are actually probabilistic models. So you feed in data, and it will tell you the probability that data was drawn from the training sample. So that's very useful for example, like anomaly detection. So one of the things I'm working on now is for DESI, we have a whole bunch of like 100,000 decals, so DES images. Actually, what the data that Brice was showing you is the DESI targeting data. So that's what we're going to use to figure out what objects to take spectra of. So we have 100,000 of these spectra, and a really small fraction, 0.1% of the exposures just have weird artifacts like scattered light and stuff like that. And so we're using probabilistic models to figure out when an exposure just does not look normal. Okay, so we trained it on a whole bunch of normal data, of which we've got lots, and then we're going to, and we're actually getting human labels for the for a small fraction of our data, and then we use a probabilistic model to automatically go through all of the 100,000 exposures and find the ones that don't look right, because they have low probability of being from a population of normal exposures. Okay, so I just scratched the surface on this, but here's a good blog post that I recommend for that gives a nice kind of overview of how all of these different models, all these different buzzwords relate to each other, kind of, and in the the theoretical framework that they live in. Okay, so finally, kind of where do I recommend you go next? So in these lectures, I try to introduce what the main ideas are of doing practical Bayesian computing, and also then how that relates to unsupervised deep learning. And we've seen that there are some theoretical ideas that keep cropping up, and they're really key here. So like stochastic processes, measuring the distance between two probability densities with like KL, or the symmetrized Jensen-Shannon, or this even Earth mover Wasserstein metric I talked about. So all the examples I show you are toy problems, more for pedagogy, and that means that all of the code is pretty easy to understand, and you can read it. It's all in the notebooks, and those are working. But to go beyond simple examples, to really use this in your research, what I recommend is that you take some time and learn a probabilistic programming language. Okay, so when you hear that, you're probably thinking, well, I've already spent all this time learning Python. I don't want to learn a new language. So this is not a new language. This is just what they call it. This is still Python, but it's really, it's working at a much higher level of abstraction, which I guess why it's called a language. It's kind of like a domain-specific language built on Python. So what this means is it's a language for, it's a vocabulary for building probabilistic models that explain your data. And the key idea here is that you specify the models independently of how you're going to learn from the data, the inference. The models and the inference are completely separated. And then once you've built your model, you can build the model once, and then you can try different things. You can do a Markov chain, or you can do variational inference, or other methods, right? So you build the model, and that's just like model equals blah, blah, blah. And then you can say, learn using variational inference, or learn using Markov chain Monte Carlo. These things are fully Bayesian if you want to take a Bayesian approach, so understand about posteriors and priors. And they work at a high level of abstraction, which means that the primitives here are random variables and probability densities, okay, not float 32s or tensors. So the classic probabilistic programming languages are things called Stan and PyMC, which is now in its third iteration. But today, if you're starting with this, I would recommend you use either of these two. So if you're already drunk the TensorFlow Kool-Aid, then there's an add-on package to TensorFlow called TensorFlow Probability. That used to be something called Edward, which was actually written by a grad student, and then it was Google hired him, and then no longer had time to work on it. So, so TensorFlow Probability is kind of where is the probabilistic programming language for TensorFlow, and then the one for PyTorch is called Pyro. They have pretty similar ideas, so it's once you've learned one of them, it's pretty easy to work in the other one. But that, for serious work in this area, and these can do variational inference. They can do all different kinds of Monte Carlo. They can do VAEs. They can do GAN. So it's really kind of a high level. It's doing all of this stuff where you care about being Bayesian and keeping track of uncertainties, but leveraging all of the power of TensorFlow and Pyro to take full advantage of cloud computing and GPUs. So. Okay, so I hope this has given you a good foundation, and that you will go on and look more at this stuff. So all of the material for the two, let's see. I want to show you where the lectures are. Yeah, so this is the GitHub page that has the lectures. So these links here will actually show you the slideshow. And then these links here will show you the notebook, so you can see some of the code. that I hid in the slides that actually makes all the plots and examples work. If you actually want to run these yourself, you just need to clone the repository. In order to get the right packages, I set up an environment file, so you can just create a conda environment that has the packages that I used, and then you can actually have the examples should all work for you. If you want a deeper dive into some of the topics, there's something like 20 notebooks, kind of all at a similar level to what I showed here, and for the course that I teach at UCI, the grad course, Machine Learning and Statistics for physicists. So finally, some of you asked about how to do the slideshows. So actually, I had been using Jupyter Notebooks for several years before I realized you could do this slideshow thing, but it's pretty convenient. So this link here gives you a little overview of how to do it. There's 2 caveats as of today. So first of all, Jupyter is going through this major transformation. It used to be Jupyter Notebook, and that's what I used for the slideshow. But really, all the developers now are working on this Jupyter Lab environment, which completely changes a lot of the programming model. So a lot of the old stuff, like slideshow, has not been ported over yet. So it works. So right now, you'd have to use the old Jupyter Notebook. And the other thing is that, notice I never actually ran any Jupyter code in here. So it is basically read-only. That's an obvious shortcoming, and there's actually a package called Rise that's designed specifically to allow you to edit and run cells on the fly. I tried it, and it doesn't work very reliably. I certainly wouldn't stand up here in front of you and try and get it to work. So yeah. So and if you find errors or you have suggestions, you're welcome to email if you have kind of research questions. But also if you had a bug and you're too polite to found a mistake and too polite to tell me, you can just create an issue too. So this is GitHub. So. Okay, so thank you.